work. Oh, no! Oh, great. Batteries died, and I didn't save my work. What an idiot. Oh, wait. But this has got about 100 of these capacitors. A capacitor is a device that stores electrical charge. It just saved me there because the capacitors in there released their charge for just long enough for the computer to save my work. Thanks, buddy. So, that's what a capacitor is. How does it do it? A capacitor is basically a device that has two metal plates separated by an insulator, and the charge will build up on either of those plates. It's actually more efficient to roll these plates up like a Swiss roll, so you can store more charge. That's why capacitors look like cylinders. Okay, to give you a picture though of how these work, I'm going to give you an analogy. So every capacitor has something called a capacitance. That is the amount of charge it can store per volt across it. In this analogy, these beakers are representing the capacitance of the capacitor. My muscles are representing the voltage, which is like the energy you give to the charges. And these marshmallows are representing the charges, which is good because marshmallows are completely disgusting and there's nothing better that you can do with them than just shove them into a beaker and throw them in the bin. So anyway, let's say I apply the same amount of voltage to each of these capacitors. Right, I'm putting the same amount of energy into each one. Well, if I do that, then I can store the same amount of charge in each of them, because it's the same capacitance and the same voltage. What two things could I do, therefore, to store more charge? Thing number one, I could increase the voltage. Effectively, that's like giving the electrons more energy, and I can pack them in more tightly and fit more charge in, like this. The second thing I could do is I could increase the capacitance. In that case, I could apply the same amount of voltage to each one, but because this is a bigger capacitance, it can store more charge. The way that's represented in an equation is Q equals CV. Q being the charge, C being the capacitance, right? So the bigger capacitance, more charge, and V being the voltage. The more energy you give to the charges, the more charge you can store. Okay, that's just an analogy. Let's have a look at a genuine capacitor here. So I've got a massive capacitor, and I'm going to put 4,000 volts across it. I am literally putting my life on the line for your education. So this is quite a big emotional moment. I think you should be pausing the video right now and contemplating on that for a couple of minutes. Go ahead now. I must be strong and carry on, 'cause I know I don't belong here in heaven. So I'm assuming that you've paused the video. If you've not, then you're basically a terrible person. So I'm just increasing the voltage here to 4,000 volts, and then I'm going to discharge it by connecting the two plates together with this metal rod. We'll see what happens. Nah, got you worried. A lot of charge is stored. Now, one other thing you need to know about capacitors is graphs. How they charge and how they discharge. And you need to know about voltage graphs and current graphs. I'll just zoom in here. So let's start off with voltage graphs. Voltage graphs are actually quite easy to remember. The voltage across a capacitor when it's charging is going to start off with 0. No charge, no voltage. But gradually, as that capacitor charges up, the voltage, which is this graph here, is going to increase until it reaches a maximum, which will be the voltage of the battery. And if you were to switch this circuit, then you could show what happens to it as it discharges. Okay, so in this case, it starts off with a big voltage, but it gradually releases those charges and acts a bit like a draining battery, goes down to zero. So voltage graphs are easy. Increase when it's charging, decrease when it's discharging. But what about the current graphs? Well, a good way of thinking about this is imagining like passengers arriving at a train station. Let's say you've got a lot of passengers at Waverley and they're all trying to get on the same train, and the train starts off empty. Well, to start off with, the flow of passengers onto that train is going to be quite big. But gradually, as the train fills up with passengers, it's going to be harder to get any more passengers on, unless you like take a running jump or something. And eventually the flow of passengers is going to reduce. And that's exactly what happens with a capacitor. As the charges build up on it, it gets harder and harder for any more charges to get on the plates. And so the current goes down. But what happens when it's discharging? Well, let's go back to the train analogy. When a really packed train arrives at Waverley Station, everyone is really fed up with everyone else's body odour, and so they all try and flood out of the train as quickly as they can. And to start off with, there's a lot of people going out, so the flow is quite big. But again, what happens? Eventually the flow starts to slow down as the train empties. And that's the same as a capacitor. When it's discharging, the current starts off high and goes down to zero. Right? Notice that the zero axis is actually up here. So the current is decreasing whether you charge or discharge a capacitor. It just does that in opposite directions. The other thing you need to know about these graphs is what effect a resistor and capacitor has on how quickly the graphs change. So just remind ourselves what the graphs look like, which is this. If you decrease the resistance in this circuit from 1000 to 500 ohms, look what happens to the graphs. The voltage graph increases more rapidly. The current decreases more rapidly. That's because if you decrease the resistance, the current goes up. And if there's more current, the charges can build up a lot more quickly. Let's think about what happens if you change the capacitor and you make it smaller. What happens? Again, the voltage builds up more quickly and the current drops off more quickly because it takes a lot shorter time to charge a small capacitor than a big one. Now, if those graphs are slightly confusing to you, let me finish off with an analogy. I quite like analogies. Let's say it's the morning and you are having your bowl of fruit and fibre, as we all are. Best meal of the day. It's like the opposite of marshmallows. And you've got two bowls because you're really hungry, but with one bowl you have a big flow of milk. In the other bowl you've got a small flow of milk. That would be like having a big current and therefore a small resistor. And that's a small current which would be obtained from having a big resistor. Which bowl is going to fill up faster? Obviously the bowl on the left. Okay? So with a smaller resistor, the capacitor is able to charge more quickly. Okay, let's say this time you have two bowls, but you've run out of bowls because you've eaten so much fruit and fibre, so you're having to have a small bowl as well. Small bowl and a big bowl, that's like having a small capacitor and a big capacitor. This time you keep the flow of milk the same. Which one is going to fill up to the top faster? The small bowl. So a small capacitor will charge more quickly than a big one. Okay, So what I've done just now is I have increased your capacitance to learn. All you need to do now is charge into your revision. I am so funny. So funny.